Hey, welcome to Chemistry with Mrs. Mays. This podcast is all about molecular geometry. We're going to look at structures that go beyond just simple tetrahedral geometry shapes. So, hold on. It's going to get crazy. Vesper theory is the foundation of everything we're going to do with our electrons and our molecular geometries. So, you should know that Vesper stands for the valence shell electron repulsion theory. Basically, it states that groups or domains of valence electrons that are associated with a central atom will orient themselves so as to minimize the repulsion between them. Remember, electrons are all negatively charged, so they don't like to be near one another. They all have the same charge. So they're going to orient themselves around the central atom so that they don't push away too much. They're going to get as far apart as they can. And when we say domains of electrons, what we're talking about here could include lone pairs or bonding pairs, or it could be the multiple pairs of electrons that are in a double or triple bond. Lone pairs are the ones that are going to take up the most space, because lone pairs always take up more space than bonding pairs. By lone pairs, we mean electrons that are non-bonding. Balloons would do this too. If I were to take two balloons and attach them to a central attachment point, like tie their ends together, then they would naturally line up in 180 degrees so that the balloons don't get crowded together. But if I attach three balloons, then they line up in a plane, in all triangles all in the same plane. It's called trigonal planar arrangement. If I were to put four balloons together, then I would have a tetrahedron. And that's the shape that we started with in class when we were looking at molecular geometries, just four domains of electrons. But we could also have five domains, where we would have, say, a triangle here around the equator, and the axis would be straight up and down. So that is how five balloons would arrange themselves. The same would be true for five domains of electrons. And then if you have six balloons, then you would have like two tetrahedrons sort of smushed together, where we have the top and the bottom, and then the arrangement around the middle. So that's what balloons do, and it's also similar to what electrons do when we put them around a central atom. And geometry is really important. The arrangement of electrons in space around the central atom have a powerful influence on the chemical and physical properties of a compound. Like whether or not the electrons are bonding pairs or non-bonding pairs will influence important things like the melting point and the boiling point of a substance. The more polar the bonds are, the higher the temperature has to be to melt it or boil it. It will also affect the solubility of the substance in water, the pH, and the conductivity, and lots of other properties that you might think of. So let's look at two electron domains. What we mean here is we have two groups of bonding electrons connected to a central atom. In this case, the shape will be called linear. The bond angle for a linear structure is 180 degrees, a straight line, right? So it looks kind of like this, where we have the central atom called A, and then I have my two other atoms attached to it, and the electrons spread as far apart as they can get, so that's 180 degrees. Some examples of compounds like this would be beryllium chloride. Remember, beryllium has an incomplete octet, so it doesn't have to have 8 electrons around it to be stable. So there's beryllium chloride, where beryllium's in the middle, the two chlorines are 180 degrees apart. Another example would be carbon dioxide. We drew carbon dioxide in the podcast on molecular structures. So it has double bonds between the carbons, the carbon and the oxygens. Here are the double bonds. And then the oxygens on either side will stay as far apart as they can, 180 degrees from one another. So that's the kind of geometry we get with two electron domains. For HCN, it can get a little trickier because we have three things to consider. Which one's going to go in the middle? Well, we know hydrogen can't be in the middle, so it's down to the least electronegative, and that would be carbon. So we put hydrogen, then carbon in the middle, and then the nitrogen with a triple bond. That way everybody's got an octet. The carbon and the nitrogen, and then the hydrogen, of course, is happy with only 2 electrons. Here's another picture of that same molecule. So hydrogen cyanide is going to have 10 electrons, and they're all going to spread out as far as they can because I have 2 electron domains. Even though there's a triple bond here, it's considered 1 electron domain because the electrons are occupying the same sort of space, and then this is my other electron domain for the total of 2. So we're referring to lone pairs, bonding pairs, and non-bonding pairs around the central atom. If we have 3 electron domains, then we can have a couple of different geometrical possibilities. So let's look at a shape with all of the electrons in groups that are bonding pairs, and then we'll take a look at what happens when we have non-bonding pairs or lone pairs. So if I have all of my groups bonding groups, then we get the trigonal planar arrangement shown in the first picture with all of these domains occupied by another atom to bond with. But if we have a domain where we have a non-bonding pair, then that changes the shape. So instead of having 120 degrees for the bond angle, now this bond angle is going to get squished by the lone pair electrons that occupy more space than a bonding pair does. So we have a bond angle that is less than 120 degrees. Some examples of these include boron trifluoride. We've drawn similar atoms like this before. So there's the BF3, again an incomplete octet, right? We might also have SO2. Let's draw a picture of that one so that you can see a structure with lone pairs. So we'll start by counting the valence electrons. Sulfur has 6 and oxygen has 6. There are 2 oxygens, and so I need a total of 18 electrons in my structure. We'll put sulfur as our central atom because it has the lower electronegativity. And then I want my oxygens to have an octet first, but I know sulfur is also going to have an octet. So I'll start here. So there's 2, 4, 6, 8, 10, 12, 14, 16. And then to get 18 electrons, I need 2 more. Where am I going to put those? Well, I can't put them around any oxygens, and if I make a double bond, that doesn't solve my problem. I still have 2 more electrons to put somewhere. So I'm just going to put them on my central atom because sulfur did not have an octet yet. So by putting a lone pair on the sulfur right here, then I get 8 electrons around my sulfur. But that turns my trigonal planar shape into a bent shape or an angular shape. So we call this bent because these electrons that are non-bonding are going to push the bonding electrons so that our shape ends up being more like this. So the sulfur and the oxygen angle gets squished by the lone pair that's up here on top, and then this will be less than 120 degrees. So there's sulfur dioxide. If we have 4 electron domains, then we are looking at the tetrahedral arrangement of the electrons and the derivative shapes from the tetrahedral. So the shape that you see depends on how many bonding pairs and how many lone pairs are present. Here's some examples. The tetrahedral is the place that we started with in class when we were building the models. The bond angle between bonded atoms is 109 degrees. And the example that we used here was methane, CH4. But if we were to take one of those atoms away and have a non-bonding pair, like we do with ammonia, then what we would see is this arrangement where instead of having a bond angle of 109.5, these lone pair electrons squish the bond in and make it a little bit shorter than that at about 107 degrees instead of 109.5. Now, if we have two non-bonding pairs, two lone pairs of electrons, that's going to be similar to what we have with water. In fact, that's exactly the kind of shape that water has. The two hydrogens are attached, but then there are two non-bonding pairs that remain with the oxygen. So this bond angle is going to be squished by two sets of lone pairs so that it has only 104.5 degrees. So the examples that we looked at in class were methane, ammonia, water, and then we also looked at hydrogen chloride. This one still has 4 electron domains around my chlorine atom, but one of those electron domains is in this bond here with hydrogen, so this makes a linear shape. So we have one bonding pair, and then we have 3 non-bonding pairs, or lone pairs. So that makes a linear shape. And of course, that bond angle is 180 degrees. Suppose that we had 5 electron domains. In 5 electron domains, then the central atom would have to be an expanded octet, right? So it has to belong to period 3 or greater, where there are empty d orbitals to put those electrons in. So where there's 5 electron domains present, 3 of them are arranged in the trigonal plane. These are called the equatorial groups, so they sort of make a triangle around the middle. And then up and down, we have the axial groups. So the equatorial groups are making a triangle here in the middle. The axial groups are arranged up and down. And in any of those groups, we could have either another atom or we could have a non-bonding pair of electrons that are taking up that space. But wherever the non-bonding pairs of electrons will be, they will influence the shape and thus the properties of the substance. So I have 4 examples for each of the 4 different shapes. The trigonal bipyramidal is the shape that we get when all of these are bonding pairs. So we have bonding pairs on the equatorial plane and on the axial plane. An example of that is phosphorus pentachloride. So 5 chlorines arranged around a phosphorus. Remember, phosphorus is in row 3, energy level 3, so it has access to 3 d orbitals and it can have an expanded octet. Now suppose we have something like sulfur tetrafluoride where I have 1 lone pair on my central atom and then 4 other ligands attached to it. So these non-bonding pairs are still going to be taking up space. They're going to push everything out of its way. So the resulting shape is a seesaw. If you can imagine, so here's the teeter-totter that the little kids are sitting on, and here's the fulcrum that the teeter-totter rocks around. That's why it's called the seesaw shape. Next we have the T-shaped molecule, where you have 2 lone pair electrons, and the bonding pairs are the only ones that you actually see because we can't really see lone pairs, we just see the influence that they have on the shape. So that makes a T-shaped molecule when there are 3 bonding pairs and 2 lone pairs, like in chlorine trifluoride. So in your note-taking guide, you'll need to be sketching up the shapes of these, of the sample Lewis structures, you do not have to sketch the pictures of the ball and stick model. We'll be building those in class. Finally, if we have 3 non-bonding pairs, 3 lone pairs of electrons, then look what happens to your remaining bonded pairs. They line up in a straight line. So we're back to a linear shape, like in xenon difluoride. So push pause, draw your Lewis structures for these 4 molecules into your note-taking guide so that you can keep track of what is a seesaw, what is T-shaped, what is trigonal, bipyramidal, and how do we get a linear shape when there's 5 electron domains. This is important stuff for doing advanced molecular geometry. Now, when there are 6 electron domains, this is almost easier because everything's sort of evenly spread around, pointed toward the corners of an octahedron. So instead of having seesaws and T-shapes, we have this sort of square in the middle where we've got these corners, and then we have some that are on top and some that are on the bottom. So that's the octahedral shape. That's the way that we can get the electrons as far apart as possible when they're 90 degrees apart. So now let's look at a situation where we have a lone pair and all you have left is the square here and then one that's sticking up on top. The bottom one is just lone pairs, so we call that one square pyramidal. But if we take this one away and all we have is lone pairs on the top and the bottom, then the shape looks like a square. Finally, we can get another type of T-shape if we have 3 lone pair electrons around the axis, and then we have the up and down, and then just one corner left, so it looks like a T-shape again. And then you know what happens if we take all of the parts of the square away, and that leaves just the top and bottom atoms to bond, then you end up with a linear molecule again. How about that? We'd have 6 electron domains and still get a linear molecule. Let's look at some of these. For example, we could have sulfur hexafluoride. This one we've drawn before in the other podcast about molecular structures. So look, here's our sulfur hexafluoride, where every pair of electrons around the sulfur is a bonding pair of electrons. Now, of course, fluorine still has lone pairs around it, but since they're not around the central atom, they're not affecting the overall geometry of the molecule. So this is the shape that we would call octahedral, because all of the pairs around sulfur are bonding pairs of electrons. Now let's look at bromine pentafluoride. For bromine pentafluoride, we would start with 7 electrons around bromine, right? And then 7 electrons around each of my 5 fluorine atoms. That gives us 42, right? 42 electrons to find a home for. Well, let's start by putting the 5 fluorines around our bromine. Okay, so there's my 5 fluorines. Now let's give the fluorines an octet. So I have 10 electrons shown, then I go 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, and 40. And I'm still left with 2 electrons to find a home for, right? So where should we put them? Well, I can't make multiple bonds with fluorine, and I can't fit any more around the fluorines. It's going to have to go right here on my bromine. So here's a non-bonding pair of electrons that are going to take up a lot of space. So my shape becomes one that has 5 bonding pairs and 1 lone pair. That's going to result in the square pyramidal shape. Our last one is the ion tetrachloride, which carries a -1 charge. So of course we have to use brackets to put around the polyatomic ion, and the iodine having 7 electrons And the chlorine having 7 electrons, the only way to accommodate all of these electrons plus the one extra for the anion is to put 2 non-bonding pairs around the iodine. So where I've got 4 bonding pairs and 2 non-bonding pairs, the shape is going to be square planar. So these are my equatorial electrons, and then these would be my axial electrons, being like straight up and down in the 3-dimensional plane. So of course these are easier to visualize when we build the models, and that's exactly what we're going to do in class. But now you'll have a cheat sheet in your handy packet to help you distinguish what the geometries are. So if there's a geometry that's tetrahedral, on your final exam, you're going to have to know those without looking at your cheat sheet. But for the geometry quiz on Friday, you can use your cheat sheet. You're welcome. All right, see you in class.